lesson today. Does anyone have any questions that they would like to go over from what we started taking a look at with 4.5? I would say the classwork, but I forgot to upload it, which I will do momentarily. But any questions from what we looked at yesterday that we would like to revisit, take a look at here again? No questions? We felt good up until the definition of permutation? What's up? Extrapolation? Yeah. Do you mean combinations? No, that's not something that we're going to cover. I mean, as far as just like extrapolating, like generalizing a result. I mean, that's something that we've done a fair bit in this class, but we'll revisit it later. But no, that doesn't tie into what we're looking at here. Probably not today, but you're more than welcome to send them an email and see if they're free. All right. No questions? We feel good? All right. Cool. So yesterday, just as a bit of a recap, we looked at permutations, the idea that if we wanted to figure out the number of ways that we can select an object where the order in which that selection is occurring matters to the end result. So thinking like if I am picking out members of a tennis team and the order in which I select that individual corresponds to the court that they are going to be playing on, then we had this kind of formula for this NPR, which was equal to n factorial, just the number of ways that we can arrange our starting number of players or objects or what have you. And then what did I have to do to this? If I'm only going to choose, say, 5 individuals out of like a team of 10, what do I have to do to my total? So we have a certain number of objects being ordered. I'm saying that we want to take a small subsection of those objects, the first however many, the first R, as is the case. What do I have to do to n factorial in order to factor in that I am only taking a small subsection and only caring about the order of a tiny piece of n? So we divide by that n minus r factorial. What did n minus r factorial represent? That was the order of the things that weren't chosen, right? The number of ways that we can shuffle the tail end of our kind of set of numbers or set of whatever. And we divide it away because we're saying that the order of not being chosen doesn't matter. It doesn't matter whether you're not chosen first or whether you are not chosen last, whatever. Ultimately, what matters is that you are not chosen. Whereas being chosen, the order in which you are chosen potentially does matter. We looked at this example where because the rank of all 5 mattered, we had 5 different objects being arranged. There were none of them that we wanted to get rid of, right? We cared about the order of every single one of those particular slots. And so we saw that this was really just 5 factorial or 120. But if we look at a slightly modified version of this question, where rather than caring about how every single location is ranked, we only care about the top 3. So all of a sudden now we only care about who's coming in first, second, or third. First of all, does the ranking change if I pick one restaurant for first versus picking that restaurant for second? Is that a different ranking? Yeah, that's a different way to rank the restaurants. And of these restaurants that we are looking at, or of these kind of positions that we're looking at, how many of those slots do we actually care about in terms of order? The first 3. And so how many do we not care about? 2 of them at the end. And so what am I going to do to my 5 factorial? Divided by 2 factorial, which ultimately is 2. In this particular case, 2 factorial is 2 times 1, which is just 2. In order to get that this was 120 divided by 2, that's 60 different ones. Yes. Looking at I'm going to skip the one example. I want to look at the bottom example here. In this case, we have 42 people who are eligible for being a particular class officer. In this case, we'll think of being chosen as meaning being chosen first as being like assigned to president, being chosen second as being vice president, and so on. The question is, how many different ways are we able to select these for officers? So again, the first question, which I want to kind of be primed to think about, does the order in which these individuals are chosen or sorted matter for the overall result? Yes, right? Being chosen first has one person being president, versus if that person is chosen second, then they're vice president, versus if they're chosen third, then they're treasurer. That is a different result each time. And so order here matters. And so how many total students am I effectively mathematically shuffling? So 42 overall. So we start with that 42 factorial. And then how many of those 42 slots do I not care about in terms of order? How many do I care about? I care about the first 4. So how many do I not care about? The remaining 38, exactly. (48 factorial divided by 38 factorial. We could compute that directly. That's not too difficult to do. But we can also just go 48 factorial divided by 38 factorial equals an add. I don't know what is up with today. The calculator has not done this prior to this, but has decided that today is the day for adds. Cool. 2,686,320 ways to do this. Sure. Which is the same as 42 times 41 times 40 times 39. Right. But the main kind of idea that I want to impress here is the idea that we can remove shufflings. We can get rid of ways that we can shuffle certain spots by dividing it out of our overall total. Right. That's kind of the crowning piece that we see here. All right, questions with our first example here. Questions with permutations. We'll call these basic questions with basic permutations. We're going to look at a slightly more complicated one here in a second. Okay. This page is just the same thing. It had my notes had you like going through and actually like writing out the sample spaces and like crossing off the one. No, we're not doing that. We're counting efficiently, not counting horribly and then showing us how to count efficiently. We're counting efficiently here. That's what we're going for. So let's look at a slightly trickier example. Let's look at a slightly more complicated example here. For this, we want to know the number of ways that we can arrange the letters in the word statistics to get a new string of letters. So I skipped a page. We're looking at permutation with repeats. Okay, let's make some observations about the word statistics. 10 letters.
Oh, I counted
the question mark. Did you count the question mark? Yeah, you're good. So we have 10 letters. And then Liz, what did you observe here? I think 3 S's, 3 T's, and then 2 I's. Yep. Okay. So the kind of main idea here is if I take this particular arrangement of the letters in statistics and I swap around the S's, right? Maybe I take this S and put it here, and then maybe this S goes here, and then maybe this S goes here. Have I generated a different string of letters? No, it's going to be exactly the same. So I can shuffle the S's as much as I like, and that should be totally fine. Okay. What about the T's? What if I start like trading around the T's? Like this T goes here, this T goes here, and maybe the other one just stays the same. Is that going to create a new string of letters? No. Okay. And the I's as well, right? I could shuffle the I's between the two. There are only 2 different ways really to do that. And that's not going to create a difference. How many ways do I have that I can shuffle for a particular string here? How many ways do I have that I can shuffle my 3 S's? Mm, 3 factorial. 3 times 2 times 1, because what's happening every time we fill a slot? We're losing an S, right? We're using up a particular S whenever we use a slot. So there are 3 factorial arrangements for these particular S's, and we're saying that all 3 factorial works out to be 6. All 6 of those arrangements are identical. Likewise, how many arrangements for our T's do we have? 3 factorial for our T's, and how many for our I's? 2 factorial for our I's, which is just 2, right? We can swap them back and forth. Cool. So then how do I figure out the overall number of that I have to take away, right? How do I work this out? There is temptation here to look at this and say, oh, there are 8 slots that I'm allowed to shuffle, and it's not going to change anything. So I'll just divide away 8 factorial, and we'll be done there. What's the problem with that? What's the problem with assuming that I can just divide away 8 factorial and call it a day? So it leaves us with 2 options. Those 2 options would be like the A and the C, maybe the position of the A and the position of the C, where like those are the ones where we can't really swap them around all that much. So that's maybe not necessarily an issue. there's something very fundamental here that creates a big problem for us. So that's true, but we have more swaps than just 3 factorial, right? Like I can swap all my t's, and I can swap all my i's, and I can swap all my s's. The main issue is that 8 factorial only works for 8 slots that are indistinguishable from one another. For instance, 8 factorial would be saying that I could take the s and the t and swap those and get the same thing, right? It shouldn't matter what order they come in. But it's a little bit more nuanced than that. It doesn't matter what order it comes in as long as an s is replacing an s, or as long as a t is trading with a t. But a t can't trade with an s. We can't do that. So we have to eliminate each of these orderings, each of these shufflings individually. So how many total ways can I arrange 10 letters? 10 factorial. And then what should I do to this 10 factorial to get rid of the shufflings that we are seeing here? How can I get rid of the s's, and then how can I get rid of the t's, and then how can I get rid of the i's? How do we so factorial is multiplications. How are we going to undo that? We're going to divide by 3 factorial, which gets rid of the orderings of the s's. And then we still want to be dividing. So dividing again, or in this case, multiplying the denominator by another 3 factorial, which gets rid of the order for the t's, and then dividing out by 2 factorial to get rid of the i's. So 3 factorial to deal with this, another 3 factorial to deal with this, and then a 2 factorial to deal with this. And this is, of course, highly generalizable, right? If we wanted to look at the way of dealing with permutations with repeats, all we are simply doing is taking n factorial over like r1 factorial, r2 factorial, so on, where r1, r2, and so forth are the number of repeats for a particular value. Right? So for the s's, there are 3 s's. We need to divide out by 3 factorial. For the i's, there are 2 i's. We need to divide out by 2 factorial. So okay. What is 10 factorial divided by 3 factorial, 3 factorial, 2 factorial? How much? 50,000, I think 50,400. Yeah, perfect. So still a lot of ways to do it, even though there are also a lot of overlap. Questions with our repetition. Okay, let's take a stab at a second example here, looking for the number of different ways to arrange different types of books on a bookshelf in a bookstore. So we've got 6 hardbacks that are the same, 3 paperbacks that are the same, and then 3 boxed books that are the same. How many total books am I trying to line up on the shelf?
6 plus 3.
Yep, you got it. 12 books total, which means how many are my total just arrangements of books before I start thinking about repetition? 12 factorial ways to just line up the books. What do I have to do to this 12 factorial? 6 factorial, which takes care of the hardbacks, and then 3 factorial, which takes care of the paperbacks, and then another 3 factorial, which takes care of the box books. Very nice. Very, very nice. And we could plug this into our calculator as well. Use parentheses when you're entering into the denominator. Otherwise, it'll think that you're trying to multiply. That sounds right.
18,480.
Yeah, that sounds right. 18,480. Very good. How do we feel about our permutations? Not too bad? Permutation, there are a couple of ways that you can define it. I would define it most basically as the number of ways to select R objects from a group of N where the order of selection matters. Where the order in which the objects are being selected matters, yeah. Right, so for instance, being picked for our statistics here, having the T come first versus the S come first changes the arrangement of the letters. Or if we were thinking about like coming in like first, second, or third place for a competition, it doesn't matter after the podium what place you come in per se. But if you come in first place versus second place, that's a different result of that. Sure. Okay. So permutations are our way to count when the order of selection ends up mattering. But we could certainly think of examples where order doesn't matter. For instance, let's say we had like an Olympics qualifying event for a particular race. At that point, what matters is less about coming in first or second and more about making the top cut. Right? More about going on to the Olympics than how you are doing in that particular event. So then rather than wanting to worry about who is coming in first, who is coming in second, we might just want to say who's going to the Olympics, right? What result do we actually care about? Where the order in which we select the people who are going matters a lot less. You could think about this as like going to, for swim meets. If we are trying to figure out a team of 10 to take from 30, it doesn't matter the order in which the 10 are selected. And it also doesn't matter the order in which the 20 are not selected. All that matters is whether you are selected or not. Right? So that order element stops mattering as much. If I want to make the order of the ones being selected not matter anymore, if I want to get rid of that from my kind of permutation equation, what should we do? What should we do to our permutation equation to make it so that the order of being chosen is no longer a factor? How have we been getting rid of order up until this point? Dividing by that number factorial? Okay. So how many for our how many objects are we selecting for this particular setup? Well, just for like the generic setup, right? For this one, we said we have n objects total. We want to make it so that the order of the ones that aren't picked, the n minus r, the leftovers, that doesn't matter. So we divide that away. What else are we going to need to divide away to make it so that the order of the ones being chosen also doesn't matter?
Did we go back to the?
I'm using this as a scaffold to get an equation. Okay, let's maybe do this a little bit more concretely without our n's and our r's. If I have 8 objects here, 8 places, or I guess this is what, 7, whatever, can't count. And I want to know the number of ways that I can either finish to the left of the line or the right of the line. It doesn't matter the order in which the objects are arranged on the left of the line. It doesn't matter the order in which the objects are arranged on the right of the line. How many different arrangements do I have total? Just overall, 7 factorial. Okay. What do I need to do to the 7 factorial? 5. So what does the 3 factorial represent? What am I getting rid of? The order of the first 3. And then what else do I need to do to the 7 factorial? Divided by the 4 factorial to get rid of the order of the last 4 as well. And that's a combination instead of a permutation. All right. So NCR, very similar to permutation, where we are now still selecting R from a group of N, but now the C is just telling us that order doesn't matter. This just means order doesn't matter. Is going to be really the exact same formula, right? We're still taking our n factorial objects. We're still dividing away the order of the stuff that doesn't get chosen. But now what's the extra piece that I need to divide away here? The order in which I am choosing. An additional r factorial is going to need to be divided away. All right, if I'm selecting 3 objects, the order in which I don't select the 4 objects doesn't matter, divide away 4 factorial. The order in which I don't select the 3 objects doesn't matter, divide away 3 factorial. Okay, let's take a look at an example here. We have a seamstress trying to make a dress out of 2 colors. We have 5 colors to choose from. First and foremost, am I going to get a different dress if I first choose blue and then choose red versus first choosing red, then choosing blue? No. So does the order in which I pick my colors matter at all? No, it's not going to change the outcome. It doesn't change anything. I'm going to use a combination here rather than a permutation. If I have 5 different colors, how many total arrangements for those colors do I have? So that's what it's going to break into. But just before we start worrying about being selected, not being selected, 5 factorial. Okay. And then what do I have to do to this 5 factorial? Okay. What does dividing it by the 2 factorial get rid of?
The first 2 you choose.
The order in which I'm choosing the first 2 colors. And what does dividing by the 3 factorial do? The 3 I didn't choose. It gets rid of the order that I am not choosing the colors. Yeah. So think of like the order in which you are being selected can sometimes change an outcome. So the ones that we've looked at so far were like being selected for like a class representative, where the 4 options were president, vice president, treasurer, and secretary. Being selected first would put you in the president position. Being selected second would put you in the vice president position. So all of a sudden, the order in which you're being chosen is also important to think about rather than just whether or not you are chosen. Whereas here, it doesn't matter if you pick blue first or red first. All that matters is which color you actually pick. So it takes away, like, we don't want to think about the order in which we're choosing things. We want red blue to be the same as blue red. So we divide it away to get rid of that order. Yeah, so order is literally talking about like the order in which I am pulling the objects, like first, second, third, fourth. Yeah. Yeah, good question. Order can mean different things in math, so that's a fair question. Other questions? No, why not? Because we're multiplying and multiplication is, yep, commutative. Yeah, A times B is the same as B times A. But funny here that even the order within it doesn't matter. Commutative. That's the other one's not the word. So commutative is the property of I can multiply in any order that I want. Yeah, or add in any order or do whatever, right? Which doesn't always apply. Matrix multiplication is a fantastic example of multiplication that is not commutative. Sets that are commutative under a particular operation are called abelian. So much fun stuff that we could talk about that we're not going to. Okay, let's take a look at, again, a slightly more complicated example here. I'm looking down at the drama club example that we see. So in this case, we have 7 girls and 5 boys. We are trying to form a committee of 3 girls and 2 boys. So first of all, being on the committee, does it matter whether you are chosen first to be on the committee or last to be on the committee? No. All that matters is, are you on the committee or not? Okay, so does the order of selection matter for this one? No. Combination. Cool. All right. We are going to basically be dealing with this as like an and statement from before, where we're going to use the fundamental counting principle to take 2 simpler arrangements. And what do I do when I have my 2 simple arrangements? Like when I have my number of sizes and my number of flavors, what do I do to get the number of outcomes? Multiply them together, right? So 3 sizes, 8 flavors, 24 different combinations of the 2. Okay, so we're going to do ways to select girls for the committee, ways to select boys for the committee, multiply them together, ways to have a committee. Sure. Okay, so for the committee of, let's focus on the girls first. How many ways can I arrange the girls? How many girls do I have, and how can I arrange them? 7 girls, so it's 7 factorial ways to arrange them. Yep, so dividing by 3 factorial. Why do we divide by the 3 factorial? So there are 3 on the committee, and we already said order in which they're selected for the committee doesn't matter, so we get rid of that order. And then what else doesn't matter? The 4 that aren't chosen, right? Not being chosen first is the same as not being chosen second. So divide away another 4 factorial. Works itself out to be, you can plug it into your calculator if you like, this works itself out to be 35. Okay, for our guys, how many guys are we lining up? We have 5 factorial ways to line up the guys, and then what do I have to do to this 5 factorial? So 2 to get rid of the 2 boys that are chosen, not getting rid of them, but getting rid of the shufflings that I can have of those 2 boys. And then divide away the 3 that are not getting chosen, which you can plug into your calculator as well, works itself out to be 10. By the way, you can go through your calculator and plug in 7 factorial divided by 3 factorial, 4 factorial. That's fine. Nothing wrong with that. I can also go to NCR and just watch an ad really quickly to, do my job. And this is, we said 7, and we want to choose 3, 35.
Where do you see?
So if you go math, scroll over to prob, and then it's NCR. If you have an older version of the calculator, so if you're not using one of the classroom set, it'll require you to first enter N, then plug in the NPR, and then enter the number that you would like. So depending on whether you have like the TI-84 color, whatever this newer one is, versus the like original TI-83 or TI-84, you might have to enter it in a slightly different way. So just mess around with it, figure out what you got to do. Okay, and what did we say we need to do with these two numbers? Multiply them together. So 35 times 10 tells us there are 350 ways to make this committee. Absolutely, it will be on the test. Yes. More than that, it'll be on the quiz that you have on Monday, which we'll talk about later. Okay. Questions on combinations, permutations, factorial, all that stuff. Feeling okay? Okay. 4.6, which is the last section of Unit 4, which we will be finishing today, is going to be a little summary of everything that we've talked about. Cool. That's nice of me. 4.6 is going to be, it's nothing new conceptually. The reason why we want the stuff from 4.5 is the ability to count complicated sample spaces really, really quickly. So these tools that we're seeing, these counting tools, will let us figure out the denominators of our probability, the numerators of our probability. We're going to use them to actually figure out the likelihood of certain events. Sure. So for the denominators, the thing that we need to keep in mind for our probability, we are looking for the number of total possible outcomes. And then the numerators, number of ways that we can get success, which often can come from like the fundamental counting principle that we did with the multiplication. Okay, so looking at our first example here, we're told that a waiting room has 6 Highlights magazines, 8 National Geographic magazines, and we are selecting 2 of them. Pausing here. From this setup, do we feel like the order in which we are choosing the magazines is going to affect the final result? Probably not, right? Maybe if it then went on to say, find the probability that you first select a Highlights and then select a National Geographic, then all of a sudden order matters, right? And then that problem gets insanely complicated, and we're not going to do that because I don't even really know how we would begin approaching it. It's very, very tricky. But we don't care about that, right? So order is not going to matter. We are going to use our combinations here, which is nice. All right. Actually, there are a couple of ways that we could do it. It's not too bad. A little tricky for sure, but not too bad. We need to then figure out the total number of ways that this whole selection process can play out. So what are we actually doing? Like, what is the event that is going on? Picking 2 magazines. And so how could I figure out the number of ways to pick 2 magazines out of 14 if order does not matter? So 14 factorial is part of it. That would be like the 14 objects being arranged. How many are we choosing? We're choosing 2. Does the order in which we choose those 2 matter? No. Okay. And then how many are we not choosing? 12. Does the order in which we don't choose that 12 matter? No. So we haven't factored into the whole like 6 and 8 thing yet. We're going to take a look at how we would do that here in a second. This is just saying for our general setup, the number of ways that we can pull 2 magazines. Some of those magazines will be both highlights. Some of them will be both National Geographic. Some of them will be a mix. These are just the total number of ways to do it. Yes. How many magazines are left over after I pull 2? Does the order of those magazines that are left over affect the result that I'm looking at? Does the order of the stack of magazines that are left over affect the 2 magazines that I'm looking at? Does it affect my outcome? No, so I need to divide it out. Divide out the 12 factor. Another way to write this is just 14 choose 2, right? Okay, so then our numerator needs to be the number of successes, right? We need the number of ways that from this 14 choose 2, we need the number of ways that we can pull exactly 1 highlights and exactly 1 National Geographic. Okay. Not too horrible. How many ways, or how could I figure out the number of ways that I can pick a single highlights magazine? Think of this as like the boys and girls example. What are the number of ways to figure out the number of girls? What are the number of ways that I can arrange the boys? And then we're going to combine them at the end. Perfect. That's beautiful. So Merrick here is saying 6 factorial, which is the total number of highlights magazines that we can choose from, or ways to arrange the highlights magazines. We want to choose one of them. The order in which we choose that one doesn't matter, sure. And we want to divide away also the order of the ones that don't get chosen, which is the same thing as 6 choose 1. Yes. Yep. Yeah, exactly. Okay, so this is the number of ways that we can get one of the highlights magazines. Okay. How could I find the number of ways to get the National Geographic? What is that going to look like? Yeah. Very good, which is the same as 8 choose 1. And what am I doing with these 2 values? Number of ways to get 1 National Geographic, and I am multiplying them together. All right, fundamental counting principle. I have 6 different outcomes for the first. I have 8 different outcomes for the second. That gives us a total of 48 out of 91 outcomes. What's up? Get 1 National Geographic. Yeah, so this is, you can plug it into your calculator. This works out to be 91. This works out to be 6, and this works out to be 8. If you want to not worry about the complications, I had someone in my previous class ask if I recommended like plugging in like this entire thing into the calculator. Like, should I try and plug in this whole behemoth? You can. If you do it correctly, it'll spit out the right number. You could also figure out what each individual piece is equal to and then just combine them in post. That's also fine. But however you want to do it, whatever is going to lower your likelihood of making a mistake. How are we feeling? Not too horrible? Try to make it a little worse while we're here. Okay, everyone's favorite deck of cards that we all are incredibly familiar with and know masterfully the contents of and are ready for the Texas Hold'em game that will be Wednesday's test. All right. That was a joke. But also, yes, you need to know cards for the test. Yeah. So yes and no. Yeah, you do. I do expect you to know these numbers. Sure. Or you can learn the information that's in the packet. Either way. However you want to do it. All right. So looking at our first example here, we are trying to figure out the probability of getting 3 jacks. We're going to say for this, because it gets complicated, and we'll look at that complication later at the end. We're going to say it's exactly 3 jacks. So it's not going to be like at least 3 jacks. We're going to say we want to know the probability of getting exactly triple jacks in a 5-card hand. We'd expect it to be fairly unlikely, right? That should be a pretty rare hand. All right. So first and foremost, we need to figure out our sample space here. What is the action that we are doing? Drawing 5 cards, right? So we're taking the deck, flipping 5 cards up without replacement, right? Just flipping 5 cards up, looking to see what those 5 cards are. How can I figure out the number of ways that I can flip those 5? Well, first of all, before we get into that, does the order of the cards affect whether or not we have 3 jacks in hand? No, it doesn't matter if I get like a jack first and fourth and fifth versus second, third, and fourth. What matters is the cards themselves. So the order in which I'm getting these cards does not matter. So we'll do that combination thing again. Cool. Needing to figure out the total number of ways to deal 5 cards from a 52 card deck. What is that going to be? Okay, so yeah, 52 factorial. Sorry. 52 factorial over. How many cards are we choosing? 5 factorial, right? Just dealing 5 cards. And then 47 factorial. Or we could write this as 52, choose 5. Plug it in your calculator, 2.599 million ways to do this. A lot. A couple. Okay, and now we're going to treat this exactly like what we saw before. So we need to know the number of ways that we can get 3 jacks, the number of different ways that that can show up. How many options do I have for jacks? We can arrive at it that way. How many jacks do we have in a deck? 4 jacks in a deck. Okay, and we want to see how many of those? We want to see 3 of them. So, other way. Yeah, exactly. Or 4 choose 3. This is the number of ways that we can get 3 jacks. Sure. Am I done? Is that my hand? Finished? What am I missing? I'm missing 2 cards. Okay. What do I know about those 2 remaining cards? They can be anything except, well, they can be anything except for those 3 jacks, but also they can just be anything except for, if we're getting exactly 3 jacks, then they can be anything except for jacks in general, right? We know that those final 2 cards aren't going to be jacks because otherwise we'd have 4 jacks. If this question were at least 3 jacks, then we'd have to deal with the possibility of, okay, what if one of those other 2 cards is a jack? We'll look at how we do that later. But for now, we know that those 2 cards should be coming from how many cards are not jacks in our deck? 48 of the cards should not be jacks. And how many are we picking? 2 remaining cards. How many cards are not jacks in our 5-card hand?
Oh, there are 3 jacks.
Yes.
So if you pick 1, you will not. Also.
So we know the 3 of our hand are jacks, which means that 2 cards in our hand are not jacks. Yeah, exactly. Exactly. Couple of things to note. So to our point here, what do we notice about this 3 and this 2? They add up to 5. It's the total number of objects that we are working with. Exactly. So that 5 that we see there. Okay. What do we notice about the 4 and the 48? That's going to add up to be the 52 total cards that we're pulling from. That's a nice little pattern that can theoretically reduce the difficulty of this quite a bit. Should we take a look at another? Oh, well, I guess we should plug this into our calculator. If you plug this in, it works out to be 0.00, how many zeros? 0017. Small. Like we said, very rare. 0.17% chance. Yeah. Very, very rare. Triple jacks, pretty rare hand. You could figure out each of the individual values. So you could do 4 choose 3 and then 48 choose 2, multiply those together, and then do 52 choose 5, and then divide that.
You don't do that. And then what we do is we go to math, and then we go over to.
You could also enter in what Merrick was saying earlier of the, if you prefer this, Wesley, you could also do the 52 factorial over the like 5 factorial, 47 factorial, and that also would work. That would also work as well. Either way you want to do it is fine. Yep. Okay, so let's take a look at our second example here. Again, 5-card hand. How many different ways do I have to make a 5-card hand? Only 5 ways to make a 5-card hand? 52 choose 5. Okay. In this case, we want to know the likelihood of getting 4 aces with those 5 cards. Very unlikely. Okay. So what is the, what options do I have for aces? How many aces do I have to choose from? I have 4 aces to choose from. And how many do I want? 4. Okay. And then how many cards that are not aces do I have to choose from? Well, I want 1, but how many do I have to choose from? 48 not aces, and we want 1 of those. I believe, double check me, this works itself out to be 0.000018. Exactly as you see it there. No, for C4, for choose 4, right? If you go to math, PRB. You'll, in this case, because of how small the number is, you get that like e to the -5 or e -5. Do we know what the e -5 is telling us to do? Do we understand that one? Yeah, perfect. So if we see like it ends up being like 1.8 e -5, this is telling us that we slide 5 places to the left of the decimal. So 1, 2, 3, 4, 5. Decimal should be right here, and each of these should be zeros. In other words, the number of zeros should be 1 less than whatever that number is. So 1, 2, 3, 4 zeros, and then my first digit, and then we run. Mm-hmm. You can, sure. Slide the decimal back over 2 places. A lot of decimal sliding here. This would be 0.0018%. Very, very, very unlikely to get quad aces in a hand of 5.
So, again, the problem, my number 5 is really phase 4, is really four, C4. So why not? 4, 5.
4, choose 4. We have 4 options for aces, and we want to choose all 4 of them.
I would have never done it. So,
Cool. Yeah, we're gonna do another one right now. Can do a whole bunch right now. This is like the only example that we're gonna do, and we're gonna do it over and over and over again. This is 4-6. Welcome. It's the same problem over and over and over and over and over again. It has different flavors. It's all the same. Okay. Sure. Yeah. Okay. You'll probably want to stick around to see the very last example that we're gonna do. Do you know how long it'll take?
He said it shouldn't. Should take less than 5.
Okay, if you want to run now, then that might be a good thing. Okay, so we are trying to figure out the probability of getting 2 queens and 2 kings. We're again going to stick with the like exactly 2 kings and exactly 2 queens, and then 1 mystery card from 5 cards that are drawn. So again, just like before, what is our sample size? How many ways do we have to draw 5 cards from a deck? 52, choose 5. 2.599 million. A lot of ways. All right. We're going to figure out the number of ways that we can pick a king. How many options do we have for what our king could be? How many options within the deck do we have for what our king could be? 4. And how many of those do we want? 2. How many kings are there in a deck? Okay. How many options do we have in our deck for what the queens could be? 4. And how many do we want? 2. And then how many options for not being a king and not being a queen do we have in our deck?
So it would be 52 minus 8. Or no, right?
Yeah.
Okay. Let me get the calculator out. All right, what is it?
Yeah, 44. And how many of these 44 do we want to see? One.
Good listen.
Works itself out to be 0.00060, something like that, or 61 or something like that, or 0.06%. All right, questions here. Almost done. One more that I want to look at. Slightly tricky iteration of this problem. Okay, I'm skipping to the last problem here. These are all, it's all the same. These are all the same problem over and over and over and over again. One little twist that I want to talk about at the end here. Let's actually we'll take like, I don't know, 2 minutes, maybe less, probably less. Figure out the setup for this first example of all of them being defective. Right? Actually, we're only going to take like a minute on this, right? So figure out just the setup. You don't need to plug it into your calculator, solve it just yet. I just want to see the setup for what this is going to look like.
All of them are defective?
So the first, we're just doing the first one for now. Find the likelihood that all of the ones that are sold are defective. Mm-hmm.
It says exactly 2.
I'm looking at the final page.
No, that's like.
Yep. Very last example.
Actually, it wouldn't be 21. So it would be 3. Okay, 3, 2. I cannot do that. Choose
19 choose. How many from the 19 are we going to sell?
No, 3. 0.
0. Yeah, 19 choose 0. Would work. 19 choose 0 is just 1. So like technically you don't need to include it, but I really like that you include it. I was going to include it in mine as well. Absolutely.
Yeah, thank you. That's why my NCT score is a 20.
Okay, let's take a look at our setup here. So, what is our sample space size going to look like? So this is 24. And how many are we selecting? How many are we selling? 3. So 24 choose 3. Okay. If all of them are defective, how many options do I have for defective remotes to sell? How many for defective remotes? I have 5 defective remotes that I could sell. And how many do I want to pick? I want to pick 3 of them. And then I do want to just highlight this because it's the continuation of the logic that we had. Merrick did a good job of noting this. How many do we have that are not defective? We have 19 that are not defective. And how many of those are we going to sell? 0. 19 choose 0 is just 1. There's only one way to not choose any of the 19, and it's to not choose any of the 19. So this works out to just be 1, but I do want to include it here just so that we can kind of see it's a very similar kind of analog to what we had before.
Quick question.
Yeah.
So, look at the fact that are defective and 3 are sold at random. You want to sell 1 to 5, you want to sell 3 times 19 are defective. So you want to sell 0.
Yeah.
But my question is, why is 5C3 times 19 0? Why is that the numerator? And why is 20? Why is it 24 remotes? No, 24C3. Why is that the denominator? But why did you arrange it like that specific?
So what does 24C3 represent? What does 24 choose 3 represent?
24 remotes.
Right, but what does 24 choose 3? What does that specifically represent? What does that value represent?
All the remotes where 3 are sold.
So all of the ways to sell 3 out of the 24 remotes, independent of how many are defective, independent of how many work. That's just the total number of ways to sell 3 of the 24 remotes. Okay, so that's for our probability, that's the total number of outcomes, right? So that's all of the possible ways that we could possibly see this going. Okay. The numerator is an application of the fundamental counting principle, where we say that, hey, I have this kind of mini result here, which is the number of defectives that I'm selling. I have the number of ways to sell a defective, rather. I have the number of ways that I can sell a working remote as well. Multiplying those together gives us the total number of successes. So that's why it's arranged numerator denominator like we see.
So
yeah.
It's because 24 is all the outcomes.
It's because the denominator represents all possible outcomes, and an outcome in this case is the selling of 3 remotes. So this is all total possible ways to pick 3 remotes to sell out of 24. Importantly, does the order in which we sell the remote matter? No, which is why it's 24 choose 3. Good question. Very good question. If you want to mess around with it, I would recommend listing out the number of options that 5 choose 3 actually are. So maybe name the remotes or come up with another scenario where it's things that are distinguishable from one another, and play around with that. Why would that be the numerator? It's not a bad question to explore. Okay, final one that we're going to look at. The probability that at least one of our remotes is defective. This gets to be a little bit tricky, because what are the outcomes that I could see that would fit that bill? What are the ways that I could sell remotes that would fit that condition? No. I'm just saying, what are the ways that I verbally, descriptively, how can I fulfill that condition of selling at least one defective remote? Give me an outcome that sells at least one defective remote. I sold 1 defective and 2 that work. Right? I'm selling 3 remotes. Selling 3 remotes. So maybe I sold 1 that is broken and 2 that work. What else could I do that would fit that bill of being at least 1? 2 defective, 1 that works, or I could, what's the last one? 3 defective. Cool. Okay, so I'm either able to sell 1 that's defective, 2 that work, or I could sell 2 that are defective, 1 that works, or I could sell 3 that are defective and 0 that work. What do I do with my OR probabilities? I'm going to add them together. Is it possible to both sell 1 defective remote and 2 that work, and also sell 2 defective remotes and only 1 that works within 1 3 remote session? Am I going to have overlap, basically, in my results? Is there an outcome that I can get that both sells exactly one broken remote and also exactly two broken remotes? No. Okay. So there is no overlap. These are, what's our word? Mutually exclusive events. Fantastic. Okay. So mutually exclusive events, don't need to worry about the overlap. I am going to absolutely right. I'm going to add all these probabilities together. So we want to figure out the probability of having one broken and two work. We want to figure out the probability of having two broken and one work. And we're going to find the probability of having three broken and zero work. Okay. What is our setup for, we're just going to go through each of these. What's our setup for having one broken and two that work? What is this going to look like? Very good. Divide it by 24 choose 3. Perfect. Beautiful. Very snappy. For having two that are broken and one that works, what's that going to look like? Perfect. And for having zero that work, well, we already did that, right? That's the one we calculated for part A. That was 5 choose 3, and we can include it while we're here. Might as well, right? 19 choose 0 divided by 24 choose 3. And what are we doing with each of these probabilities? Or statement, we add the probabilities together. Which is how we would do this with if it was like at least two kings where we could get a third king or a fourth king as well, we would do this exact same thing. All right, questions with Unit 4? Okay, yeah, so let's talk about what next week is going to look like here. We'll pause our recording here.